has an activity of 5 millicurie, which has an activity represented as 5 millicurie. It's number milli, that is 5 into 10 to the power minus 3. Curie is not the SI unit of activity, so we need to convert it to vector. It is 1 curie is equal to 3.7 into 10 to the power 10 vector or disintegration per second. Let it be. And solving this, what do we get? 5 into 3.7. So we get it as 1.85 into 10 to the power 8 BQ, that is vector or disintegration per second. So 5 millicurie is the activity given. Half-life of sodium 22 is 2.6 years. So that is again T half is equal to 2.6 years they have given. But actually it's not the SI unit of time, so we need to convert it to seconds. So this will be 2.6 into 365 into 24 into 60 into 60. So you can calculate this value directly, put it in online, then you can go with direct answer. This comes out to be 8.2 into 10 to the power 7 seconds. So 8.2 into 10 to the power 7 seconds. Okay, this is the information given, and also Na, that is Avogadro number 6.023 into 10 to the power 23 atoms. So we need to calculate the mass of sodium. Let us say M. We need to calculate the mass of sodium 22. For that, the formula we have is M is equal to number of atoms in the given sample divided by the Avogadro number and the molecular weight of the sodium 22. So this is the standard equation we need to remember in order to calculate the mass. That is the number of atoms in the given sample divided by Avogadro number and the molecular weight of the given sample. So guys, if you look at this formula, we have Na and this is going to be 22. So we have these two values, but we don't have a number of atoms. So we need to calculate the number of atoms first. So how that can be done? Let's make use of the data given. So N, let's use A is given. If we look at the relationship between N and A, we have activity A is equal to lambda N. Activity A is equal to lambda N. So let's rearrange this. What happens? N is equal to A by lambda. N is equal to A divided by lambda. Again, if you observe, the lambda value is not given in the numerical. So what we can do? Let's make use of this half-life. There is a relationship between the lambda, that is disintegration constant, and this half-life, that is half-life is equal to 0.693 divided by lambda. So you can reverse this. So what we get? N is equal to A divided by 0.693 T half whole divided by T half, and shift upwards, that is T half. 0.693. Let's find it out. Okay, 1.85 divided by 8.2 into 0.693. We get it as n is equal to 2.2 into 10 to the power 16 atoms. So we get the value of number of atoms in the given sample is 2.2 into 10 to the power 16 atoms. So let's find out the mass of the given sample. M is equal to n, that is number of atoms. We have just calculated. Avogadro number and molecular weight. This is 2.2 into 10 to the power 16 whole divided by 6.023 into 10 to the power 23 and 22. And solving this, we get, let's, okay, 2.2 into 22 whole divided by 6.023. So 8.035 into 10 to the power 16 minus 6. So the 16 minus 23, we get it as minus 7. We get it as minus 7. You can also write it as 8.034 into 10 to the power minus 7 grams is the mass of the given sample. And you can also convert into micrograms like that. So let's finish with this one. We have calculated the mass. That's what they are asking for. Determine the mass of sodium 22, which has an activity. So activity is given, half-life is given, Avogadro number is given, and they are asking us to calculate the mass. And using the data and using different equations, finding out the relationship between them, we need to calculate the mass of the given sample, and is coming out to be 8.034 10 to the power minus 7 grams. So this question was asked in March 2015. We got the mass as 8.034 10 to the power minus 7 grams. The standard unit of mass is kg. Let's convert it to kg. So it has m is equal to 8.034 10 to the power minus 7 grams means 10 to the power minus 3 kg. So minus 7 minus 3 is minus 10 kg. So we have calculated the mass of the sodium 22 using the given data. Let's move on to the next question. Let's start with question number 12. In the first 2 units, electric charges and fields, and also electric potential and capacitance. This question is asked in June 2019, and this is a similar question. Variables are different. It was earlier in June 2015, similar to that question. So let's solve this. ABCD is a square of side 1 meter. So let's take again square A, B, C, D of side 1 meter. It says charges of plus 3 nanocoulomb, minus 5 nanocoulomb and plus 3 nanocoulomb are placed at the corners A, B and C respectively. So at A we have plus 3 nanocoulomb, at B we have minus 5 nanocoulomb, at C we have plus 3 nanocoulomb respectively. Calculate the work done. So what we need to calculate? We need to calculate the work done in transferring a charge of 12 microcoulomb from D to the point of intersection of diagonals. So from here we have to transfer the charge, I call it as some Q naught, from D to the intersection of diagonals. So the intersection of diagonals I call it as O. So we have to transfer the charge 12 microcoulomb from D to O and calculate the work done. So the formula for calculating the work done in this case, I can write it as the charge moved into potential difference, that is Vd minus Vo. So we can make use of the formula to calculate the work done is equal to Q naught, the charge moved, and potential difference, that is Vd minus Vo. Let's find out Vd and then Vo, then we can calculate the work done. So let's start with Vd. This is the potential at D. Potential at D is due to these three charges. That is charge at A, at B, and at C. So you can write potential at D due to A plus potential at D due to C plus potential at D due to so this is B and this is C. Potential at D due to C. Let's write down the formula. K QA divided by dA plus K QB divided by dB plus K QC divided by dC. Let's proceed here. Vd. K is taken common. All the things, K is taken common. Then I am left with QA, that is plus 3 into 10 to the power minus 9, that is nano coulomb, divided by dA. dA is 1. dA is 1 meter. Next, since it is minus QB, K is taken common, plus into minus 5 into 10 to the power minus 9 whole divided by dB, that's the diagonal. So let's calculate the diagonal value. dB square, considering the right angle triangle, BDC. BD square is equal to DC square plus BC square, that is 1 plus 1, 2. So root 2, the value is root 2. Then QC plus 3 into 10 to the power minus 9 divided by the distance is 1. The distance is going to be 1. So let's solve this. That is 9 into 10 to the power 9. In all the three equations, 10 to the power minus 9 can be taken common. So 10 to the power minus 9. Then I am left with 3 minus 5 by root 2 plus 3. So this is 9. 9 10 to the power 9 minus 9 and 6 multiplied by 6 minus 5 by root 2. Let's solve this. On solving this, potential at D is equal to 22 point, the value is 22.18 volts. Similarly, let's calculate the potential at O. Vo, again the charge is moved to the point O. The potential at O is due to again the charge at A, that is VOA plus VOB plus VOC. This equation becomes K QA divided by OA plus K QB divided by OB plus K QC divided by OC. So what can be taken common in this is K and the distance are common. VO is equal to K by any of the distance. I take it as OA. Since OA is equal to OB is equal to OC, then I am left with QA QB plus QC. 9 into 10 to the power 9 whole divided by OA. OA is the half of the diagonal. The diagonal is root 2. So the half of the root 2 is root 2 by 2, and this will be 3 into 10 to the power minus 9 minus 5 into 10 to the power minus 9 plus 3 into 10 to the power minus 9. So on solving this, we get it as 6 into 10 to the power minus 9 minus 5, so 1 into 10 to the power minus 9. So finally write 2 shifts upwards, 2 into 9 into 10 to the power 9 into 10 to the power minus 9 whole divided by root 2. On solving this, V0 is equal to, we get it as so 18 divided by root 2, so 12.72 volts. So the potential at V0 is 12.72 volts. So let's find out the value of work done. So the value of work done, I'd like to write here. Let me complete this space here. Adjust with this. Q0 12 into 10 to the power minus 6, that is 12 microcoulomb, and this is going to be 22.18 minus 12.72. So on solving this, the work done, we get it as 253.43 into 10 to the power minus 6 joules. So we get the value as 253.43 into 10 to the power minus 6 joules. So basically, if you remember the formula, we get the required values. Work done is equal to charge moved into potential difference, that is VD minus VO. VD we need to calculate first. So VD we get it as 22.18. Then VO, the potential at the intersection of diagonals, we get it as 12.72. And finally the work done is charge moved and the potential difference. So we get 253.43. Okay. Let's start with the question 30 from the first 2 units. This question is asked in March 2020. This is a question similar to June 2014. So what is the change exactly is, here we have 5 microcoulomb and minus 5 microcoulomb. In June 2014 it is 3 microcoulomb and minus 3 microcoulomb. This is the only change given this test charge. So let's start solving this question. 2 point charges QA is equal to 5 microcoulomb and QB is equal to minus 3 microcoulomb are located at A and B, points A and B separated by 0.2 meter in vacuum. Okay, so I take this, let's take this point A and the another point B. So here we have the charge 5 microcoulomb, that is QA. We have QB is equal to minus 5 microcoulomb. So the separation is 0.2 meter. The distance, let us say, R is equal to 0.2 meter between the 2 charges. Okay, in vacuum. So epsilon we can use it directly. What is the electric field at the midpoint O of line joining 2 charges? Let us say the midpoint O here, equidistance from A and B. They are calling this point as O. They are asking what is the electric field at midpoint O of the line joining 2 charges. So Okay, this is question A. Let's solve this question first and then we can go for the question number B, sub question. They are asking us to calculate the electric field at the point O. So in order to calculate the electric field at point O, we consider a positive test charge. The resultant electric field due to charge at A, that is positive, and test charge is positive, the resultant electric field will be towards B. So I call this one as electric field at O due to A. And the next one, QB minus 5 microcoulomb. The electric field which is causing at O, this is positive and is negative. It will be, the resultant electric field will be towards B. So this is, I call it as electric field at O due to B. Okay. So you can see that both the electric fields are in same direction. So we can add them. Finally, the electric field at O will be equal to EOA plus EOB. And one more thing, we can come up with that EOA is equal to EOB. EOA will be equal to EOB since see, OA is equal to OB. The distance is same. QA is equal to QB. The charges are same. The quantity of charges are same. And the electric field is directly proportional to the charge and inversely proportional to the square of the distance. Since the distance and charge are same in EOA and EOB, so we can write it as 2 EOA or EOB can be taken. Let's solve this. 2 into K QA divided by OA square. Let's proceed. Electric field at O will be equal to 2 into 9 into 10 to the power 9 and charge is 5 into 10 to the power minus 6 whole divided by OA, that is 0.1, half of the distance between AB, 0.1 whole square. 0.1 can be written as 10 to the power minus 1 square, that is 10 to the power minus 2. So what we get here? 45 into 2, 90. So 90 into 10 to the power 9 minus 6 plus 2. So 10 to the power minus 1 square is minus 2 and it shifts upwards becomes plus. So 11, 9 plus 2, 11, 11 minus 6 is 5. So I can write 90 into 10 to the power 5 Newton per Coulomb. 90 into 10 to the power 5 Newton per Coulomb. This is the electric field at O, that is the point between line joining the two charges. Let's solve the sub question. If a negative test charge 2 nanocoulomb is placed at O, so we place a charge of 2 nanocoulomb. What is the force experienced by the test charge? It's very simple. They are saying Q is equal to 2 nano 10 to the power minus 9 coulomb. We place this charge at O where there is electric field of 90 to 10 to the power 5 Newton per Coulomb. They are asking the force. So force F is equal to, the relation between these two is force F. Force on charge Q will be Q into electric field at E. So that is 2 into 10 to the power minus 9 into 90 into 10 to the power 5. So I am solving this. 180 into 10 to the power minus 4 or else 1, 2, 3 0.018, let it be 180 into 10 to the power minus 4 Newton. So this is the amount of force which acts on the charge, kept at point O in presence of an electric field due to the charges A and B. So we get the value 180 into 10 to the power minus 4 Newton. So guys, along with this numerical, we complete the numericals first two units, that is electric charges and fields, electric potential and capacitance. The March 2020, okay, next the September 2020, the supplementary happened in September 2020. Then they have asked me a question which is very much, which is as same as the earlier question that what we have discussed in 2014, March 2014. So we have discussed the same question which is asked in supplementary exam of September 2020. So that's why I avoid that question number 40. So this completes the numericals from the first two units. So in the next video we will be starting from the